అర్థమైంది. కామెంట్ చేశారు ఎక్కడ మీరు?
ఏది
చేసేసి అంటుంది రేపు దిగుతుండే రేపు.
ఆయన ఏదో చెప్తాడు దీని గురించి ఇంపాసిబుల్. Good evening. I welcome you all to this problem solving session. First of all, my best wishes to all the students who are preparing for ISRO entrance. Let us solve some analog circuit questions. Go through the question. The circuit is with an ideal operational amplifier with plus or minus 10 volt supply. The output voltage is, you are asked to find the output voltage when the input is 20 millivolt and 40 millivolt. This resembles to be a weighted adder circuit. So try to calculate. So this is an inverting amplifier. You can apply superposition theorem. So with 20 millivolts, your V0 is going to be minus 10k by 1k into 20 milli. So with superposition theorem, what if you ground the 40 millivolt? This is virtually zero here. So no current would flow. So this is a dummy resistor now. So minus R2 by R1 plus with 40 millivolt here 10k by 1k or minus 10k by 2k into 40 millivolt. So try to calculate this. 10 into 2 minus 200 minus 200, it is minus 400 millivolt. Option B is the right answer. So try to calculate this minus 200, 2 2s are minus 200 minus 400 millivolt. Go through the question. A BJT is having common emitter current gain. Common emitter current gain means beta. Beta is given as 100. Considering a 10 volt supply and a VB of 0.7 volts, what will be the value of RC and RB to set the quiescent point IC at 10 milliampere? 10 milli and VC of 8 volts. VC of 8 volts. So now with the given data, he is asking us to find RC and RB. So what is RC? Directly, RC is going to be 10 minus 8 by 10 milli. 10 minus 8 is 2, 2 by 10. 2 by 10 milli is RC. So it is going to be 200. So I think there is only one option where it is 200. So there is no need for you to calculate, RB, because 2000 by 10, it is going to be 200. I think option A is the right answer. So go through the question. For a class A FET power amplifier with 10 volts drain supply and 2 amperes drain current, supply voltage is 10 volts, VDD is 10 volts, and 2 ampere is a drain bias current. I bias is 2 amperes. Providing an RF load current IL of 1 ampere, amplitude, what is the DC to RF efficiency for the load resistance of 5 ohms? 5 ohms. So he is asking you to find the efficiency of the system. So how do you calculate the efficiency of a system when you have an amplifier connected to a DC supply of 10 volt and a biasing current of 2 ampere? Now this amplifier is connected to a load, the RL value is 5 ohms and IL is 1 ampere. So efficiency is generally power output by power input. Efficiency of the system is power output AC by power input DC power. Whenever we say AC power, you have to do the RMS calculation. So what is RMS? It is IL M by root 2 whole square into RL by VDD into I bias. So substitute the values now. IL is the load current here is 1 ampere, 1 by root 2 whole square is 1 by 2, RL is 5 and VDD is 10 into 2. So try to calculate this. It will be 5 by 20. It is going to be 5 ones are 5, 5 twos are 10 is 1 by 8. 1 by 8 could be 12.5%. 1 by 8. Efficiency is 1 by 8 into 100%. Into 100. So that is going to be 12.5%. It is going to be how much? 12.5%. So go through the problem once again. You are given an amplifier which has a DC power supply and some biasing current. The load current is 5 ohms and the load resistance is 5 ohms and the load current is 1 ampere. So what is efficiency of the system? Efficiency is power output by power input, right? The power input is not from the signal. Power is supplied by who supplies power? Who supplies power? power is supplied by the power supply. Okay, so who supplies power? The power supply supplies power. That is why it's called the power supply. So the power supply is supplying the power input, that's 10 volt, 10 volt into 2 ampere. So it is 1 by 8 into 100, that is 12.5%. Now, the approximate output frequency of a 555 oscillator for RA equal to RB equal to 2.2K and C is 2000 picofarad. C is 2000 picofarad. So, this is a standard substitution problem. For a 555 timer, RA, RB, when we say RA and RB, it could be a square wave generator, an astable circuit. So, in an astable circuit, frequency is 1 by T, 1 by T. T stands for the time period and it is split into T1 plus T2, T1 plus T2 and frequency is 1 by T. So, what is T1? T1 is 0.69 RA plus RB into C. And T2 is again 0.69 RB into C. So, you can substitute the total T is going to be T1 plus T2 and the frequency is 1 by T. The frequency is 1 by T. So, RA is given, RB is also given, capacitor C is also given, RA and RB, RA given RA and RB are 2.2K, RA is 2.2K, RB is also 2.2K and C is given 200 picofarad, no 2000 picofarad. So, try to substitute these values and get the frequency. I will give you a minute. So, when you substitute these values, the frequency comes to 109.3 kilohertz. So, go through this question. The output response of a diode clipper circuit shown in figure will be, the output response of a diode clipper circuit shown in the figure will be. So, you can see here the diode is on when anode is greater than cathode. The diode is on when anode is greater than cathode, or the diode is on when cathode is lesser than anode. Cathode is lesser than anode. So, it is all one and the same. Suppose this is the cathode voltage with respect to ground. It is minus VB plus Vin. So, cathode should be less than anode. Anode is at ground 0. So, what is cathode? Cathode is minus VB plus Vin. If it is less than 0, the diode is on. When the diode is on, the output, the diode is replaced by, let me see if there is any drop for the diode. No, nothing is given. So, you can take this diode as ideal. So, the diode drop is 0 volts. Once it is on, the diode is replaced by short circuit. So, your V0 is 0. Now what if it is other way around? So here you can see your Vin is less than Vb. So this is the first case. Now what is the second case? If the diode is not on, then it is off. If the diode is not on, it is off. So for Vin less than Vb, what happens when Vin is greater than Vb? The diode is off. So as you keep on giving larger Vins, suppose your Vb is just 2 volt, if you keep on giving larger Vin like 10, 15, 20, 100, so naturally you are making cathode more positive than anode. The diode is off. What will be your output? Your output is, this is Vb, you have Vin, replace the diode with open switch. So when you apply KVL here, it is minus Vb plus Vn, minus Vb plus Vn. It's minus Vb plus Vn. So, so the two states are, the output can be 0 or the output is Vn minus Vb. The output is Vn minus Vb. I can see something here, Vn minus output. So this portion is Vn minus Vb, or the output is 0. Otherwise, there is no space here. I'll take a fresh page and show you. Let us take some value of Vb. Suppose your Vb is, say for example, your Vb is 2 volt. So your Vb is 2 volt. So what happens? If your Vb is 2 volt, what is your V naught? For all Vn greater than Vb, V naught is Vn minus Vb. For all Vn less than Vb, your V naught is 0. So for all Vn less than Vb, which is less than 2, your V naught is going to be 0. Your V naught is going to be 0 for all Vn less than Vb. And what happens when Vn is greater than Vb? Suppose your Vn has a peak value of 5. So what is your V naught? Your V naught is Vn minus Vb in this range, Vn minus Vb, or Vn minus 2. So what happens when Vn is 5? When Vn is 5, 5 minus 2 is going to be 3. 5 minus 2 is going to be 3. So you can see this kind of a waveform somewhere here. So option B is the right answer. Option B is going to be the right answer. So for all Vn less than Vb, your V naught is 0. Your V naught is 0. For all Vn greater than Vb, it is Vn minus Vb. It is going to be Vn minus Vb. So, yeah. Go through the problem. I'll give you a minute. See, while preparing for any entrance exam, a student should bear in mind that during preparation, while solving problems, the best way to learn is through mistakes. So a student should not hesitate to do mistakes. The more mistakes you do, the better learning you will have. So if you are doing problems where you are not making any mistakes at all, then the learning is 0. So the best way to learn is not giving a wild guess or something, is to improve the concepts. And how will you improve the concepts? The best way to improve the concepts is by making mistakes. So at least when a student prepares, we used to tell them, try to make at least 5 or 6 mistakes a day. If you make 6 mistakes a day, or even 10 mistakes a day, so at the end of 1 month, you would have learned at least 300 new concepts. So try to prepare a little short notes. When you do the second revision, what happens is the number of mistakes which you do will reduce it. So finally, you should come to a point where there is nothing left now. You can't make any mistakes because you have learnt every area of it. So don't be hesitant in order to make mistake. The best way to learn is always to give a try. Okay? Don't rather than just keeping a wild guess of the questions. It's always better you be brave, make mistakes, and learn from them. Right? So for an N-channel MOSFET, if contention parameter K is given, 0.249 K, 0.249 milliampere per volt square. The gate to source voltage VGS, it is 2 volts. No, it's not 2, it's 2 VT. It is 2 VT, and VT is 0.75 volt. 0.75. So the current ID will be. So if a MOSFET has to behave as an amplifier, it has to work in saturation where it is K times of VGS minus VT whole square by 2. So what is K? K is 0.259 or 249. VGS is 2 VT. 2 VT minus VT whole square by 2. So 2 VT minus VT is going to be VT, and VT value is 0.75. So your ID is going to be 0.249 into VT. VT is 0.75 whole square by 2. So try to calculate this. Try to calculate 0.249 into 0.75 square. 0.249 into 0.75 square. So my calculator .140, but 0.140 there is no option. Option C. Option C is there, 0.140. Go through the question. I'll give you a minute. Both transistors T1 and T2 in the figure have a threshold of 1 volt. The device parameters K1 and K2 are 36 microampere per volt square and 9 microampere per volt square. The output voltage is the output voltage. Now you can see if both the MOSFETs are similar with the same device parameters, this 5 volt is split into 2.5 and 2.5. So your V0 is going to be 2.5 volts. But now these MOSFETs are not similar. So we have to calculate, but the only clue you have is in series current is going to be same. In series current is going to be same. So what is ID? ID is K times of VGS minus VT whole square by 2. It is K times of VGS minus VT whole square by 2. I'll change the pen. Yeah, so substitute here. What is K1? Going to be 36 micro into VGS1. VGS1 is 5 minus V0. 5 minus V0. And how much is VT? 1 volt. Whole square by 2. K2. K2 is 9 micro. 9 micro. VGS2. You can see this is V0. So your VGS2, this V0. VGS2 is V0 minus 0. V0 minus 1 whole square. So now try to solve this for V0. Try to solve this for V0. 2 gets cancelled. 9 ones are 9 fours are 36. So it is 4 times of 5 minus 1 is again 4. 4 minus V0 whole square is V0 minus 1 whole square. So that is going to be apply root on both sides. 2 into 4 minus V0 is V0 minus 1. So simple problem. 8 minus 2 V0. So it's going to be 3 V0 equal to 9. V0 is 3 volts. So 3 V0 is 9, but yeah, option C. Just go through it, see if there is any mistake in the algebra. Anurag Reddy, 3 volts, good. Sudhir, Pradeep Chakrabarti. I welcome you all. So each transistor in the Darlington pair has HFE equal to 100. What do you mean by HFE? HFE means the overall IC divided by IB. This is the overall HFE in the Darlington pair, the forward current gain. So what is the overall HFE of this composite pair? If the HFE is 100, HFE means beta. Beta is 100, which is IC by IB. Or IC is 100 times of IB. This is given. IC is how much? 100 times of IB. So each transistor has beta equal to 100. Beta equal to 100. Now you have to find the overall IC by IB. The overall IC by IB. So how do we start? If this is IB, what is IE? IE is 1 plus beta. 1 plus beta times of IB. If this is IB, the current is IC is beta times of IB. So that completes the first transistor Q1. Let us go to Q2. For Q2 transistor, base current is 1 plus beta times of IB. So collector current is beta times of 1 plus beta times of IB. So now you can apply KCL and finish this. So IC is going to be beta IB plus here beta plus beta square, beta into 1 plus beta into IB. So, what is the overall IC by IB? It is going to be beta square plus 2 beta. Beta square plus 2 beta. How much is beta? Beta is 100. 100 square is 10,000 plus 200. So, it is 10200. Option D is the right answer. Go through the problem. Now, suppose if you want to find IE by IB, then it is going to be 1 plus beta whole square, because IE is 1 plus beta times of IB. So, it is 1 plus beta into 1 plus beta times of IB. Then IE by IB is going to be 1 plus beta whole square, is it not? But he does not want IE by IB, he wants IC by IB. So, it is going to be beta square plus 200. And we know the main intention of having a Darlington pair is to have a larger current gain, and because the current at the output is large, whenever current is large, resistance will be less. So, you will have low output resistance, but you can have high input resistance. High input resistance because current is small. So, according to Ohm's law, R is V by I. So, when you have a small current, you will have a large resistance. So, Darlington pair would have high input resistance and low output resistance. Go through this problem. I will give you a minute. The main intention of this session is to tell you, is to just to build your confidence, because if you are preparing for GATE or any other competitive exam, ISRO should be easy to you, because the questions, if you see, they are moderate. They are moderate. Hopefully, you should be able to attempt if you have even a moderate preparation. The output voltage V0 shown in the figure below, the input voltages are V1 is 2.5 and V2 is 1 volt. So, you can apply superposition, or you can apply voltage division also. So, what is V0? With the help of 2.5 volt, it is minus R2 by R1, minus 2.2 K by 1 K into 2.5. With the help of 1 volt, you can take this node Vx. So, with the help of 1 or with the help of Vx, what is your V0? Your V0 is going to be 1 plus R2 by R1, 2.2 K by 1 K times of Vx. So, what is Vx by voltage division? So, now you can substitute here, where Vx by voltage division is 1 into 1.5 K by 3.3 K plus 1.5 K. So, substitute this and tell me the answer. Substitute and tell me the answer. Option C, very good. Option C, Anurag Reddy. Option C. Did everybody get option C? Minus 4.5. Everybody get minus 4.5. Option C. Go through this problem. I'll give you a minute. So, let us try to solve this. All transistors in the N output current mirror in figure shown below are matched with a finite gain beta. Early voltage is given as infinite. The expression for the load current, where is the load here? Could be this. The expression for the load current is. So, you have to give this expression IL in terms of I reference. You can see in the options I reference is there. So, the question is, how is this current in the current mirror is related with the reference current, right? And all transistors have same beta value, same beta. So, now you all know the clue is, if it is a MOSFET, for example, if it is a MOSFET, if VGS are same, then the IDs are same. If VGS is same, then the IDs are same. Here you can see the VBs are same. When VB, all these transistors have same VB, then their ICs are also same. So, you can take IC here, IC here, IC here and IC here, IC here. But you can see IC is not equal to I reference, IC is not equal to I reference, right? What is the relationship? If this is IC, this current is going to be IC by beta, IC by beta, and here there are N transistors, N transistors. So, this is NIC by beta, NIC by beta. So, let me draw it here, it looks little messy there. So, this is your I reference, okay. So, if this is IC by beta, since this is IC, so you are going to have N transistors here, N in parallel. So, this is NIC by beta, NIC by beta. So, IC by beta, NIC by beta, you are going to have N plus 1 into IC by beta. So, what is the relationship between emitter current and base current? The base current here IB is going to be IB, it is emitter current N plus 1 into IC by beta divided by 1 plus beta, because base current is always emitter current divided by 1 plus beta, divided all. Please remember, IE is 1 plus beta times of IB, IE is 1 plus beta times of IB. So, IB is IE divided by 1 plus beta. So, now you got the I reference. What is I reference? This IC plus this IB. So, I reference equal to IC plus the IB here is N plus 1 into IC by beta into 1 plus beta, beta into 1 plus beta. And what is IC? IC is IL, IC is IL. So, I reference is going to be, in the place of IC, just substitute IL here, In the place of IC, just substitute IL. See if there is any option. The place of IC. Yeah, so IC is going to be I reference divided by 1 plus n plus 1 by beta into, I think this one, option A. Option A. So, let me write here I reference equal to IL into 1 plus n plus 1 by beta into 1 plus beta is IL. So, IL is I reference divided by that value. I reference, you can see I reference divided by 1 plus n by beta into beta plus 1. So, option A is the right answer. Uma Shankar Mehta, welcome. Go through the problem. A class C amplifier operates entire cycle of input signal, half of the input signal, slightly more than half, less than half cycle. So, what do you mean by this? If you try to classify amplifiers based on the conduction angle, suppose you take a common emitter amplifier or a common base or common collector, all these amplifiers, they have a certain DC operating point over which you will find the signal. These type of amplifiers are called class A. So, this is like your common emitter, for example. So, all the pre-amplifiers or voltage amplifiers, they come under this category, class A. But if the conduction angle is only 50%, so that means these type of amplifiers have some kind of a push-pull arrangement, where one transistor will conduct for half, the other transistor conducts for the other half. Since each transistor conducts for only half, it is called class B. So, if the operating point, if you shift the DC here till here, then if the DC's line is here, what happens if you still shift it up and decrease the conduction angle less than 50%. So, if you decrease the conduction angle less than 50%, then it is called class C amplifier. Then it is called what amplifier? Class C. It is less than the half cycle. Now, these type of amplifiers are used for RF tuner. Now, you might think maybe the information is lost here, but no, the information is not lost. From this signal, you can still retrieve the original sine wave because according to Fourier series, if this is the fundamental, you will have other harmonics in this. So, by tuning to a certain frequency, you can always retrieve the original information. So, these are basically frequency selective amplifiers. They are filters, RF tuned amplifiers. And class B generally comes for audio power amplifiers. These are audio power amplifiers, and class A are generally pre-amplifiers, your voltage amplifiers. So, in the option, class C amplifier operates for less than half cycle. It is less than half cycle. The configuration of a given input of the given figure is what? This is a standard oscillator called the Wein bridge, oscillator. You can see these 4 arms, they actually form the 4 arms of a bridge network. So, this is a very standard circuit. So, if you have R here, C here, R here, C here, the frequency of oscillations for this Wein bridge oscillator, if you calculate the loop gain and make it equal to 1, and the frequency should be 1 by 2 pi RC. And if this is R2 and R1, to sustain oscillations, R2 should be 2 times of R1. R2 should be how many times? 2 times of R1. This is a very standard oscillator. The main reason we use this oscillator is for in olden days for AM radios, especially for AM radios, they used to gang the capacitors and use them to tune to a certain frequency station in AM radios especially. So, that is the reason if instead of R and C, if it is R1, R2, C1, C2, then the frequency of oscillation can be 1 by 2 pi root suppose this RA, CA, RB, CB. So, it is going to be RA, RB, CA, CB. So, by changing any component, you can change the frequency, but if it is a phase shift oscillator, then it is used for fixed audio frequencies. But this Wein bridge oscillator is used for variable audio frequencies. And you know, for high frequency of oscillations, we go for LC oscillators. Go through the problem. Okay, the transistor Q1 and Q2 are identical with large beta value. The output voltage is, if Vt is given as 26 millivolt. Now, you can see that this section is a difference amplifier, meaning the output is going to amplify the difference by a factor R2 by R1, 333K by 20K. 300. If all resistors are of same value, it becomes a subtractor. So, your V0 is going to be this node, I can take it VA and this is VB. So, VA minus VB, V0 333 and 20. V0 is 333 by 20 into VA minus VB. So, this is about a subtractor. But what is this? A grounded base transistor, this is actually a log amplifier. So, your VA, this is VB1 and here you have VB2. So, your VA is minus VB1 and your VB is minus VB2. So, your VA is minus VB1 and VB is minus VB2. So, this is VB2 minus VB1. So, it is 333 by 20 VB2 minus VB1. So, some kind of band gap. This is a standard formula, you know. VB is VT log IC by IS, this VB is also VT log IC by IS. So, what happens to log A minus log B? VB1 minus VB2 is going to be Vt log IC1 by IC2 or IC2 by IC1, VB2. So, just to substitute, you will get the answer. A simple problem only. The circuit looks a little big, but it is quite simple. So, what is IC2 and IC1? IC2 is going to be, this is IC2, is going to be, this is virtually 0, IC2 is V2 by R2, IC2 is V2 by R2. And what is IC1? IC1 is going to be, this is virtually 0, V1 by R1. So, that is it. So, you can substitute Vt is 26 millivolt, 26 millivolt. Okay. So, if you do that, you will get the answer. Just substitute 333 by 20 into 26 millivolt log IC1 by IC2. Oh, there is no natural log given here. When there is no natural log, if you want log base in terms of log base 10, then log base E, you have to divide this value. So, if you want in log base 10, you divide this by 0.43, you divide this by 0.43. So, your V naught is going to be 333 by 20, Vt is 26 millivolt log IC2 is V2 by R2 and V1 by R1, V1 by R1. And if you want in log base 10, you have to divide by around 0.43, I think. So, just divide it, let me see in the calculator. Okay, the reason why he has given 333 and 20 is because this factor, when you multiply, it gets 1 actually. So, this multiply, it gets almost 1. So, option B is the answer, option B. Just go through the problem. VB1 minus VB2. Remember, this equation is extremely useful. It is not just only in the log amplifier. Even if you're solving a problem like the Widlar's current source and all that. So, these band gap, this is suppose your VB1, this is VB2, this is a Widlar's current source. In one of the ISRO problem, he has asked you to calculate this R also. This is some I reference and this is I naught. So, then what is this? VB1 minus VB2. If you apply KVL here, if you apply KVL, this I naught into R is going to be VB1 minus VB2. What is VB1 minus VB2? A standard formula, Vt log IC1 by IC2. IC1 is I reference and IC2 is I naught. When you substitute, you will get the solution. So, these equations are extremely useful. VB1 minus VB2 is Vt log IC1 by IC2. It meaning, what is the meaning of that equation? Meaning is the BJT has a characteristics between VB and IC. VB and IC. Suppose you are working at VB1, then this current is IC1. And if you are working at VB2, this is IC2. So, if you see the gap between VB1 and VB2, this VB1 minus VB2 is proportional to the log of the ratio, log of the ratio. VB1 minus VB2 is Vt log IC1 by IC2, IC1 by IC2. Go through the problem. For a CE, common emitter amplifier, what will be the value of IE and VC? What will be the value of IE and VC? See, the examiner is very clever. He has not given any data because the equation has two unknowns here. Two unknowns. IC is not known, VC is not known. IC is not known, VC is not known, and beta is not given. If at all you want to calculate IC from IB, beta also is not given. So, the examiner thinks that IC is actually 10 minus VC by 2K. IC is, or VC is 10 minus IC into 2K. Now, since he has given options here, he just wants you to substitute them. Just substitute and see which one will satisfy. So, what if we take 3 milliampere? So, if it is 3 into 2, 6, 10 minus 6 is 4, but here it is 3, so it is wrong. So, what happens if it is 4 milli? 4 2s are 8, so it is wrong. So, like that keep calculating and see which one is the closest value, which one is going to be the closest value. So, what happens if it is 3.02? 3.02 into 2 is 6.04. So, it should be less than 4. So, hopefully, this is close. The 4.2 is also okay, but out of these two, this seems to be a closest value. This seems to be the nearest number, 3.02 and 4 volt. Now, for the following circuit, determine the output voltage V0 in terms of the input voltages V1 and V2 if A1 and A2 are ideal op amps. A1 and A2 are ideal op amps. So, this is a crude form of an instrumentation amplifier. Generally, an instrumentation amplifier is designed using 3 op amps. So, 2 voltage amplifiers followed by some difference amplifier. So, that is a very popular circuit, but this circuit also you can use it for instrumentation applications. But the problem with this amplifier is the delay. When this signal is already available, this has to experience 1 op amp delay. That is why this is not very popular in the market, but it is okay. Here this is not an instrumentation amplifier from the examiner point of view. He wants you to believe that this is a simple non-inverting amplifier, and he wants you to calculate V0 in terms of V1 and V2. So, let us do this. This is V1, you can take this node as Vx. So, what is Vx? Vx is going to be 1 plus 1k by 10k, that is Vx. And what is V0? V0 is going to be in terms of Vx minus 10k by 1k times of Vx plus due to V2 1 plus R2 by R1, 1 plus 10k by 1k times of V2. Now, substitute in the place of Vx, 1 plus 1k by 10k. So, it is 11 by 10. So, this is going to be minus 10 into 11 by 10 plus 11 V2. So, there is some factor 11 coming into picture. So, there is some factor 11 coming into picture. So, 11 is a common voltage. So, hopefully option C. A sinusoidal input which can be reproduced in an op amp without any distortion, having a slew rate of 10 pi volt per microsecond and 5 volt peak output amplitude. The maximum frequency So, this is a simple substitution problem. So, what do you mean by a slewing rate? Slewing rate is just the speed of the circuit, the slope, the rate at which the output slews from one state to the other. The slewing rate is mathematically given as the slope of the output dV naught by dt max. If it is a sine wave, the differentiation of sine should be cos, and the cos wave, whenever you take a sine wave, it's got maximum slope or maximum speed at 0 crossing. So, that is why cos 0 is 1, cos 0 is 1. So, when you differentiate this, you get slew rate is how much? How much is slew rate? So, when you differentiate, your V naught is Vm sin omega t. So, differentiation of sine would be cos, and a cos signal has got maximum slope at 0 crossing. So, the maximum value of cos is 1. So, slew rate formula is omega into Vm. So, how much is slew rate given? 10 pi volts per micro. Micro means 10 power minus 6 microsecond is omega Vm. Omega is 2 pi. Omega is 2 pi f, or f we have to calculate, into Vm. How much is Vm? Is 5. So, from this equation, 10 pi by 10 power minus 6 is 2 pi f. So, from here you can calculate f. So, pi gets cancelled, 5 2s are 10. So, 10 power 6, 1 megahertz. Option B. For the silicon transistor shown in figure below, the value of base current is See, if you don't like the circuit drawn by the examiner, you can try to redraw it. Because current always flows from a higher potential to lower potential. So, if you find a transistor like this, it's better you redraw like this. So, this is an NPN. In fact, it is a simple circuit. Base is grounded. You have 10 volts, 1.9 K, and you have 2.4 K, and the negative voltage is minus 8. And since it is silicon, you can take 0.7. So, now you can tell me what is the voltage at emitter? The voltage at emitter, 0 minus VE is 0.7, VE is minus 0.7. What is IE? E is going to be minus 0.7 minus of minus 8. Potential difference is 2.4. Now, since you know IE, you can calculate IB, because beta is there. IB is IE by 1 plus beta. So, very simple question. So, just substitute and get the answer. .11 microamp, 30.11. Okay, I think the time is up. Fine then, as I told you, during the preparation, don't hesitate to learn new concepts, don't hesitate to make mistakes. Try to make your concepts strong rather than just giving a wild guess of the problems. And because every weakness has to be converted into a strength, So the more mistakes you do, the better learning it is for you. Okay. My best wishes to you for this exam, not only for the exam, future ahead, right? Good luck to you. Thank you.